Welcome to Artificial Intelligence Foundation and Application course. Today we will look into probabilistic reason. So in this lecture we will first look for when do we need to use this probabilistic reasoning. Like in earlier stuff, when we talked about propositional logic, we we used deterministic sum, like if a happen if a happens then b happen, so a implies b, but it may not be. If you think in practical scenario, then it may be possible that not always a guarantees that b will happen, so we need to attach some kind of probability for that. So we will explore that kind of probabilistic framework in this set of lectures. So first, let us see why we need probabilistic model. So first of all, we do not have the clear complete idea about my system. So whatever stuff earlier we have seen, where we have the intelligent agent and that have the known environment, it was fully observable and it is a deterministic world. Like when we talked about when we talked about CSP or the search, then we know the complete environment and it is fully observable and also as well as deterministic. So under this framework we looked into that stuff. But now if we look into another set of problems, like if I want to see the, let's say I have a toothache, then I can say that this toothache actually implies that there is a cavity. So so toothache can be caused by cavity, but it is not guaranteed that toothache is always caused by cavity. So toothache can also imply something else. So cavity just one of them. And the thing is, then we cannot deterministically say that toothache implies cavity. There can be other reason. So toothache can be uh, caused by many other kind of stuff, like it can be because of wisdom teeth, it can be gum disease or something else as well. Now if you would like to specify the whole stuff in this manner, then the specification will become too large, and it's very cumbersome to represent. Moreover, the thing is we do not have the complete knowledge. So I can have a theoretical limitation, I can have practical limitation as well, because if I need to represent 100 such reasons here, then it will be difficult for me and I may not be aware of all the stuff. So effectively we have to enhance this kind of condition with some kind of a probability stuff. So just for example, let's say I can say that if toothache happens, then maybe with 0.75 probability there is a chance that the cavity happens. So some sort of probability we have to incorporate in that notion. So we will see more on that part. So 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 coming to this probabilistic reasoning, why it is useful. So uh, it can analyze the causal effect and can predict the outcome. So so it is definitely needed for us because we have to predict something. So it can be a question something like, given that I have cavity, and what is the chances that I will have toothache. So this can be one side of question, like I have to predict when I have a cavity, then what is the chance that I will have a toothache. The other form of reasoning is called the diagnosis. Again we will look into the causal effect same as before, but finding out the reasons for a given effect. So this question is just the reverse of the previous one, like given that I have toothache, what is the chances that it is caused by cavity. So these two questions are quite similar, but if we want to answer, then we need a different methodology to analyze this behavior or this scenario, and we will look into more this stuff in this lecture. So just to go into that details, let us first quickly look into the stuff that we need to know, which are well known from earlier courses. Like when we talk about the probability, definitely it will lie between 0 and 1. So for any probability PA, it will be lying between 0 and 1, and probability of true is 1. So true is a event, it happens. False is 0, that means never happens. And then probability of A or B is probability of PA plus PB minus P of A intersection B. And probability of A intersection B, we can also write it in this manner, like probability of A given B and then the probability of B. Or we can also write in this form, like probability of B given A and probability of A. So if we reorganize these two stuff, then we get a nice equation, something like P of A is nothing but P of A given B times PB divided by P times P of B given A, and which is nothing but the famous Bayes rule, and we'll be using this rule very frequently in the subsequent lectures. So let us look into this uh, probability stuff. So let's just look into this joint probability. So what do we mean by joint probability? So so this is a given table. This is a given table where it says that the type of vehicle and the color of the vehicle, and these values, each value basically represents the probability of that one. So this value means that given car is of type electric vehicle and it is of red color is 0.05. So now if somebody asks me this question, what is the probability of a given vehicle to be red and to be EV and red, we can simply answer this value, because this is nothing but that we are looking for EV and it is red, that we are looking for. So definitely we can answer it pretty easily in this case. Now if I ask this question, what is the probability of a red vehicle? Now if you look into this table, then red vehicle can be caused by either it can be EV or it can be SUV, it can be a sedan, it can be a truck. So all this probability basically corresponds to that it will be a red vehicle. So effectively what we need to do, we need to sum all those things. So we can write this one in this manner, which is also known as the marginal probability. Like I would like to find out the type of the color of the vehicle is red, and type can be anything. So and if we sum over this, then I will get the marginal probability that will give me the probability of a red vehicle. Now let us look into another question. So what is the probability of a vehicle to be EV given that it is red? So if you look into this one and if you look into this one, there is a slight difference. Here I am asking, like, it is an EV and red, and in this case what I am asking, like, it is EV given that it is red. So the given the color is red, what is the probability of EV? Now when we try to reason of this kind of probability given a fact, and I want to find out the probability of the of a certain stuff, then it is nothing but the conditional probability. So that means given that it is red, that means it can be red under these circumstances. So this is the probability of being red, and this is the probability of a EV. now now the thing is, we need to find out the so effectively we have to find out the probability of EV normalized with red. That means given that it is red, so we have to normalize it with red, not like any kind of vehicle. So we can use the following stuff to compute the conditional probability. So effectively the stuff, so this is nothing but this block, and this probability rate is the sum of the all the stuff. So effectively it actually means that it is normalized with red. Now let us look into independence. So two variables are independent if pxy uh, is equal to probability of x times probability of y holds. It actually means that the joint distribution factors into a product of two distribution. So effectively, what is the meaning of this? Like, you'd like to find out the joint distribution, and it is nothing but the product of the individual distribution. So if this property holds, then we say that these uh, two variables are independent. And also we can say in this way, probability of x given y is nothing but a probability of x, because it does not depend on y. So independence is a simplifying modeling assumption. So typically we will, in a practical scenario, we will find very less number of situation when the two variables will be independent, but in some cases some joint distribution can be at best close to independent, and we can approximate to independent stuff, but most of the time they will be related, and we can make some kind of a approximation out of this stuff. So now let us look into this example of independence. So let's say somebody has provided me this table. So this is temperature and the weather condition. So temperature can be hot and cold, weather can be sunny and rain, and with this set of probabilities. Now if somebody asks me this question, are T and W independent? Now if I would like to find that thing out, then what I need to do, I first need to find out the marginal probabilities. So I have to find out probability of T and probability of W. So probability of T means probability of T equal to hot, probability of T equal to cold. So effectively I have to find out these four values. So now if we look into this one, then the value here will be, so probability of T is equal to hot is the sum of these two. So effectively this value will be 0.5. Similarly P of cold is nothing but 0.5. On the other hand, if you look into the weather condition, is it sunny? Then sunny can be under this and this scenario, effectively 0.6, and the rainy, it will be something like 0.4. Now we have to look into probability of T, T equal to hot and weather equal to sunny. So if I, so which is given as 0.4 from this table, and if you look into these values, if we try to determine in this way, then probability of hot is 0.5 and it is sunny, so sunny has 0.6, so effectively I get 0.3. So therefore T and W are not independent. That I can actually conclude by computing the marginal probabilities and then looking into the joint distribution. So then we can proceed for the independence. Now independence has certain advantages. Like say I toss in fair coins. So if I toss in fair coins, then for each of the coins I will have this probability. So I can express individual stuff in this manner, which is absolutely fine. Now if I want to express the joint probability, then I have to express the whole stuff with a 2 to the power n number of rows. Here if you look into this one, I just need n tables and probably 2n rows will be sufficient for me. And but if I express the whole stuff in a joint distribution, then I need 2 to the power n number of rows, and each row will have a length of n itself. So therefore I need a significant amount of space to represent that stuff, because I have to store the whole thing. So if I can represent the probability in a independent with independent variable, then I can represent the overall stuff very succinct manner. So that is the advantage of having independence. And so what can happen is, like, sometimes we may not have this independence as such, but we can have conditional independence. Even if we have some conditional independence, still we can reduce the size of the joint distribution, or we can represent the joint distribution in a small with few number of values. So that is the advantageous part. So coming to this chain rule, like, which is another important thing that we need to know. Like if I need to use probability of p of xy, then we know that this is this value. So when we just looked into the Bayes rule, we have looked into this part. Now coming to the chain rule, this is the extension of this version. Like I have to find out the joint distribution of this probability x1 to xn. So I can proceed in this manner: probability of x1 and probability of x2 given x1. Then I can proceed for probability of x3 given probability of x1 and x2, and so on and so forth. So sometimes this formula is actually useful to represent this stuff. Coming to one of the most important point, like conditional independence, that I was talking just a little ago. Like if it is pure independence, then that is the best thing. But if it's not pure independence, we can still try to find out some kind of a conditional independence. If we can figure that thing out, that can also help at certain point of time. So let's say we look into this one: probability of toothache, cavity and catch. So something like this. Let's say I have a cavity and there is a probe that was given, that was uh, put by that was put on my mouth by the doctor, and that so that probe can get catched in the cavity, and I can have toothache. So we are just representing the whole stuff in three different events: toothache, cavity, and when the probe gets catched into the cavity. So if I have a cavity, the probability that the probe catches it in it does not depend on whether I have a toothache or not. Because this is obvious, because if I have a cavity and if there is a probe, then catch then the probe can get into the catch sorry probe can get into the cavity, but that will not depend on the toothache, because these two are independent events. But only thing is that, given so these are independent, but all of these three are actually interrelated. So what we can say, like, if it's catch means probe gets stuck to the cavity given the toothache and cavity, then definitely I can say it is independent of toothache. So I can say probability of catch is given probability of so probability of catch given cavity. And the other thing also, if you look into the other way, like there is an event catch and I don't have a cavity, so definitely in this scenario it will not depend on toothache. So probability of having catch given toothache and no cavity is only depend on the no cavity, so it is independent of toothache. So effectively if we combine these two, probably we can write this one like probability of catch given toothache and cavity, so it will solely depend on the cavity, not on the toothache. So so we would like to figure out in any practical scenario such kind of conditional independence stuff, so which can actually help us a lot in representing the whole system. So just to make it formalize, so conditional independence, it is very rare to have the full independence, so therefore we actually look for the conditional independence in most of the scenario, and this is the most basic and robust form of knowledge about the uncertain environments. So mathematically we can define in this way: x is conditionally independent of y given z, which actually means p of xy given z is nothing but p of xz given p of yz. And we can also show that if somebody gives me p of xz, p of x given zy, then it is nothing but p of xz. So this can be shown in this way, like say if I have p of x given zy, so I can compute p of x y z given p of y z, and then uh, I can say uh, p of x y given z by p of z, and this p of yz I can say like p of y given z p of z. Effectively this will get cancelled out, and this part I can say p of x given z times p of y given z from this one, and p of y given z, so this will get cancelled out, so effectively p of x given z, so that will hold. Now now coming to the important part, like once we have this conditional independence and if we want to represent a system, then we follow these steps, and the whole network that we are going to develop is known as the belief network. So what does a belief network will contain? So it contains two primary information. One is the qualitative information, the other one is the quantitative information. So in the qualitative information, what we do, we represent the whole system as a graph, and in the graph, so if it's a graph, then we will have set of nodes and set of edges. So what does the nodes represent? It represents the set of random variables. The edges basically represents the dependency. That means if there is a edge between x and x to y, and then it means that x has a direct influence on y. And the graph that we will construct out of this one will be directed acyclic graph, so it will not have any kind of cycle within it. So that is the stuff. And the quantitative information that we will represent, that each node has some conditional probability table that quantifies the effects of the parents to have on the node. So we will elaborate with an example. So what does that mean? So effectively we will have we will have two important information. One is the qualitative, which will be represented by a graph that will represent the set of random variable and the dependency between the random variables. The other we would like to express with conditional probability table, just to have the numerical information about that stuff. So let us look into this example. So consider the following knowledge base. So it is raining, or let's say it's raining, and there may be traffic if it rains, and people may carry umbrella if it rains. So these are my knowledge base. Now if I try to build a belief net, then we can construct belief net in many ways, but for the time being we'll go ahead in this manner. So so let's say it's rain, and then if it rains, then there may be traffic. So if you look into this knowledge base, then we have three random variables that you can easily identify: rain, traffic, and umbrella. And so the other random variable is umbrella. Now if we would like to find out the dependency, then if there is a rain, then there may be a traffic. So rain has a direct influence on the traffic, and if it rains, then people may carry umbrella. So rain has a direct influence on the umbrella as well. Now if I the quantitative information will be represented through a conditional probability table. So here if you look into this one, I need to specify what is the probability of the traffic given it is rain, and what is the probability of traffic it is not rain, there is no rain. And since this is not dependent on anything, I just need to specify what is the probability of rain, and I can find out the what is the probability of no rain. Similarly for umbrella, I have to specify that probability of umbrella given rain and probability of umbrella given no rain. If we specify that one, then we can find out the joint distribution as well. Now the previous example was a very simple one, small one, but there can be many complicated example, or many practical scenario can be modeled through this belief network. So this, just to give you an overview, let's say I have a car, and we would like to find out we would like to reason about certain things. Like for my car, there can be a battery which may be aged, or there may be some age for the battery. Battery can be dead, battery can have a meter, battery can have a flat, battery can flatten stuff. And then if it will basically switch on the lights, or oil light can be shown or kind of stuff. There can be many other parameters in which the system will be described. So there will be many parameters through which I can describe my system, and probably we would like to reason about this kind of stuff. Like let's say it won't start. So we would like to find out, let's say, what is the probability that it will not start. Or maybe somebody can ask, if there is no gas, then what is the probability that it will not start. Or maybe something like, if the battery is aged, then what is the probability that it won't start. Or so that kind of a queries. Or I can reason the other way that we are talking earlier, like if it won't start, then what is the probability that the fuel is blocked. So this kind of query we may need to perform, and once we have this kind of a belief network, it is easy for us to reason about that stuff. The one of the major reason is like this. So if you look into this diagram, I have so many variables, and if I want to represent the probability, then I need to represent all those stuff in a joint probability stuff, and you can easily understand that how many number of rows will be there, so which will be difficult to analyze. But if we factor out, if we find out the conditional independence, and if we just figure that thing out, then we can represent the whole stuff in a simplified manner and more easy manner. So this is just an example. Another example I would like to show on a renewable energy stuff. Like I I would like to find out, like, if I make some kind of an investment for renewable energy, how much it is profitable, or what will be the probability, or what probability I will get some kind of economic benefit, or what will be the uh, like environmental benefits or the domestic income and many other things that can be queried. So we just need to figure out what are the random variables we have and how they are dependent. And once we find that out, then we have to figure out the conditional probability table. It will be provided to you in most of the cases in this course, but if you think of a practical scenario, then you have to find out those probability using certain techniques, maybe through the real life examples, and then you can actually query on that stuff. So with this I will stop now. We'll continue more on this part in the next part of this lecture. Thank you very much.